以前他们还去买车去，太恐怖了。
Hello. Hi, everybody. Welcome back. All right. Okay, so welcome back to our data mining class on this lovely Monday. Still sunny outside because of the daylight saving time. If you're not in the US, make sure that you know we have this daylight saving time, and you might want to update your calendar for the course schedule. Okay, so today we are going to continue on our discussion on mining large graph. So still remember what we have been working on last time? Maybe let me just do a quick recap on the whiteboard. How's everybody?
Good.
Good. Still learning stuff from this course?
Well, obviously, working on homework 3.
Okay, that's good. All right, so your homework 3 is really cool. You will need to build this recommendation system from scratch, right? And although your homework number 3 will be your final project, but everything that we are going to cover and we're covering right now will be something very useful for you to improve your recommendation system. So you need to be creative for your final project. All right, so what have we been talking about? We are looking at graphs, right? So a graph, you would have nodes and you have links. And let's call this edge. This is node. Our goal is to be able to find communities within a graph. And we say communities like this and like this because they are densely connected. Okay, so this is very important. This is the pattern that you want to identify. So how do we identify this type of pattern? We introduced a concept called betweenness. This is your homework number 4. So betweenness, which means, let me just tell you, the input is this graph, and what would be the output? The output are some numbers on the edge, right? And what does the number represent? The number represent the numbers here and here and here and here represent the number of shortest paths that pass through this link. For example, let's say we have a shortest path from this node to this node. We'll use this. Then every link or every edge will have a number of 1. In some cases, like here, you have only one link In some cases, you might have multiple shortest paths. Then you have to credit a fraction of the paths that will go through an edge, right? So how do we calculate all these numbers? Well, we take this graph and we start generate a BFS tree. Remember this? And so on. So why do we need a BFS tree? Well, in this case, BFS trees tell us the shortest path from one node, from the root node to any node on the tree, right? Which is the level of the tree. If you're at level 1, your shortest path will be 1. Level 2, your shortest path will be 2. Level 3, your shortest path will be 3. And sometimes you will have this between nodes links with at the same level, and we ignore them in the tree because this does not contribute to any of the shortest paths. All right, so once you have this tree, you can start, remember we start to put 1 everywhere for every node. This represents that from root to this node or any node, there is one type of shortest path, which is for level 2, the length will be 2. For level 3, the length will be 3, okay? So from here, you start to say, all right, so I have a 1, and there's only one link above me. So this link get the number of 1. What does this 1 represent? This 1 represents that if I want to travel from the root node to this node, I will have to use this link once, right? So you have a 1 here, and for this other node, you have a 1 here, and for this node here, they have a 3. What does the 3 represent? This 3 represents that from the root node as the starting point, you have 1 shortest path, 2 shortest paths, 3 shortest paths, okay? And then you just keep propagating this number and you do this for all other nodes, you will be able to generate the betweenness numbers for every edge on this tree. Pretty cool. Now you know how to do this for one tree, you should be able to do this for every tree. So why do we have multiple trees? Well, in this case, you have 1, 2, 3, 4, 5, 6, 7, 8 nodes. So you're going to build 8 trees. Each node will be the root of the tree once. Right, once you can do that, you collect every tree, the numbers you generated from every tree, you sum up all the betweenness numbers from every tree, then you divide it by 2, you have the final betweenness number. So why do we want to divide it by 2? Well, because if we look at this shortest paths, you will count it twice. The first time it will be when this node is the root. The second time will be this node as the root, right? Well, the order doesn't matter. This could be the first time, this could be the second time, but you get the idea. You count it twice, so you want to divide it by 2. Okay, cool. So you know how to calculate the betweenness number. Then how do we use the betweenness number to help us identify communities, identify the densely linked nodes? Remember, we say betweenness is when betweenness number is high, that means this is between clusters, a link that's between clusters. So that's the Russian bridge example, right? So you look at the entire graph, you say, all right, this one has the highest betweenness, let's cut it. So I'll just cut it. Now, how many communities do we have? We have 1, we have 2, right? Originally, you have 1. So how do we know this is a community? Well, in this case, in this algorithm, we look at the connected components, right? So these are all connected, these are all connected, but between them, they are not connected. So you have first community, you have the second community. Cool. What do you do next? Well, remember here, you have 2 approaches. First one, you just follow the original betweenness number, then you find the largest number. You say, maybe this one is the largest number. I'll just cut this one. And for this community, I'll just cut this one, and so on, right? Then you have how many communities? 1, 2, 3. Okay. Then what's next? Well, we continue to cut the one with the highest betweenness number, cut it, and when do you stop? Well, you stop when every node is a community, right? So that's why we have this hierarchical structure of community. So eventually your result will look like this. This is your first community. Everybody belongs to the same community. This is your second community, second level community. You have 2 clusters. Then the third one looks like this, right? Remember? Then the fourth one probably like this, and so on. So this is approach number 1. You do not recalculate the betweenness numbers. And what's the benefit of doing that? If you notice, this is very time consuming, right? You have to build a tree for every node and you have to traverse the tree, so this can take time. So if you don't recalculate the betweenness numbers, you can save time. But at what cost? Well, at the cost that each time when you are dividing a smaller community, let's say here, the betweenness number might not be able to accurately reflect the community structure within the sub-community, right? Because your betweenness number is calculated based on the original large graph. So, which is something that you need to sacrifice if you do not want to recalculate the betweenness number. Alternatively, approach number 2, you can recalculate the betweenness number, which means every time when you have a new community, you redo this. And you base on the new betweenness number to cut your graph, your communities into smaller communities and so on. Then you're done. Okay, so this is very simple, right? The entire idea is very simple. Well, improvement in the algorithm will not be simple, but the entire idea is very simple. You find the edge with the largest betweenness number and you cut it to form communities. There is a main problem of this approach. The first one is this is very time consuming, even when you do not recalculate the numbers, the betweenness numbers. So when the number of nodes is large, this might not work. Second is betweenness in the Gervin-Newman approaches cannot identify overlapping communities, right? So you cannot have one node, let's say this node, shared between communities. So that's 2 problems. So today we are going to talk about one technique, one algorithm that will be able to solve this problem without calculating the betweenness numbers. You can still identify clusters very efficiently. Then we are going to talk about algorithms to identify overlapping clusters. Okay, and let's go back to the slides. All right, so we were here last time. We know how to generate this, right? I also show you on the whiteboard. This is not a tree, this is your dendrogram. This tells you that at the beginning, everyone is one cluster. At the end, each node is a cluster. And if you cut somewhere, you will be able to obtain this hierarchical structure of clusters. Right, so this is the final output if you cut here. So now we want to talk about this. How do we know where to cut this on this dendrogram? For example, you can cut here. Or what if you want to cut here? Then every node is a community. Which cut is better? We need to have a way to evaluate this, right? Evaluate the cut. So to evaluate the cut, we have an idea called modularity. Well, it's not we. The network communities, they have an measurement that they can use to evaluate the network structure, and which is called the modularity. Is usually written as a number q, variable q. So a community or communities is sets of tightly connected nodes, right? Remember we said these are densely connected nodes. You have many links, community 1, community 2, community 3. And this modularity Q is a measurement to show how well a network is partitioned into communities. For example, if you have very dense communities, if you cut here, if you cut here and here, and you say, all right, generate this modularity Q number for me to evaluate this community, and this community, the number will be high. However, well, we say high is relative, right? So number will be high. However, if you say, all right, I only want to treat everyone as in one large community, generate a modularity number for me, and the number will be lower than this one. It will be lower than this one. Because between these two parts of the community, the same community is not densely linked, right? And also between these two parts, it's not densely linked. Between these two parts, it's not densely linked. So modularity number will be able to tell you which setting or which cut is the best. So how does it work? Given a partition of the network into some groups, S, so this is the community set. The modularity Q is, this is the summation, this is the number of edges within a group minus the expected number of edges within the group. What does it mean? If you look at this, how many S do we have? Well, if you ask to evaluate these three communities, your S will be 1 and 2 and 3. And the number of edges within the group S, this is your observation, right? You can count it. And the expected number of edges within the group, you have to be able to estimate this as expected number, right? So how do we estimate this? This means we need a null model of your graph. So let's look at a null model. So what is the null model? Given a real graph on some edge, we want to be able to construct a rewired network. Well, the term rewired here has a special meaning. If you look at here, suppose originally you can see a graph, and that graph can look like this. Connect back to itself, maybe here, and maybe here, right? So this is a graph. This is a multi-graph. And when we say rewired or a null model, what we actually mean is we are going to cut every connection here and obtain something like this. So what are the information that we still have? Well, we have the number of nodes, right? We have 1, 2, 3, 4 nodes. We also maintain the degree, the original degree of each node, right? We know that this node has a degree of 3 because it has 3 parts. This one has a degree of 2, this one has a degree of 4, this one has a degree of 1. So this is your null model from your original graph. And why do we want to do this? Well, based on your null model, we will then have multiple ways that you can generate graphs, like the one I just showed you, or you can have another one, like if you link this one to here, this one to here, this one to here, this one to here, you have this one to here, and maybe this one to here, right? So you have multiple ways that you can generate graphs so that you can use this to generate the expected number of links between nodes in a graph. So if you are not following, that's okay. but just look at this, and once we go through the slides, might be clearer. So the expected number of edges between nodes is calculated, can be calculated as follows. Let's say you have your node I and your node J. They have their degree Ki and Kj. You have these numbers, right? Because you construct this rewired network or model, you still keep your degree. So the expected numbers between them is Ki times Kj, right? Which makes sense because expected number is to see how many possible edges that you can have between these two nodes. If the two nodes have a large number of degrees, that means there are many links going out or going into them, right? So the expected number of edges between them will be higher. So that's Ki times Kj divided by 2m. And what is 2m? 2m is here. For every node, if you sum up their degree, you have 2m. So 1 degree, so for example, if you take this, if you take all these 4 nodes, what would be your 2m? So 1, 2, 3, degree 2, degree 1, degree 4, 3 plus 2 plus 1 plus 4 equal to 11. No, sorry, 10. And this tells you that you have how many links, how many edges that you can have in this graph. 5, right? Because one edge will require 2 degrees, one from this node and the other one from this node. So the summation of the degrees is 2 times the number of edges in your graph. And if you look at the expected number again, if 2 nodes have large degrees, let's just look at the numbers. This is the numbers. If the 2 nodes I and J, they have large degrees, which means the expected numbers of edges between them can be large. However, if the entire graph also have a large number of edges, the probability that these 2 nodes would share an edge would be lower, right? So you want to divide it by this 2m. But this is just some heuristic, right? You look at the numbers and you look at the denominator, is that right? This makes sense. So if this is large, this will be expected number will be small. If this is large, the expected number will be large. Makes sense. How do we know if this is correct? Well, one way we can do is we can sum up all the expected numbers of edges between every pair of nodes in the graph. That's here. So for every node in the graph, and for every node in the graph again, right? Because you want to have a pair of nodes to be able to construct an edge. And this is a multi-graph, so I can equal to J. If you sum up their expected number, this will become divided by 2. We'll talk about divided by 2. You have divided by 2 here, and you take the 2m out from here, and you just summarize. You just sum up this. What would be the result? This part becomes what? This part becomes your 1 over 4m, and this part becomes your 2m times 2m, because the summation of the degrees from every node is 2m. And based on this, the number is m, so you know that the expected number of edges in the entire graph is m, so which is true, right? So this is how you will be able to validate if this expected number is correct. And the reason why we want to divide it by 2, because if you look at here at the beginning, you are doing every node in the graph, you are doing every node in the graph again, so you will count an edge twice, once from I to J, and could be from J to I. So there's a question, can you explain a little bit on nodes and edges? What do you mean? Can you be more specific?
Well, I'm just a little bit confused on what does the red dot mean? A node, right?
This is a node in a graph.
And the edges means the black connections, or?
Okay, so if you have a graph, you have 2 very important things. One is node, 1, 2, 3, 4, and the second one is edges. And since we want to calculate the expected number of edges between nodes, the first thing that we want to do is to cut the edges to generate a null model. This means we maintain the degree of each node, but we do not know how each pair of nodes connect to each other, right? We do not know if this is connected here or this is connected here. And we're going to use this to calculate the expected numbers of edges between nodes. Does that make sense?
Yeah, sure. Thank you very much.
So if I give you guys a very simple example, we can say this is a social network. I say John has 3 friends. We cut all the friendship connections. The only thing that we know is John has 3 friends, Mary has 2 friends. Andy has 4 friends, David has 1 friend. And we want to know if John and Mary, how strong their relationship can be. In this case, if you have more than 1 edge, if you have 1 or more edges, you have strong relationship, right? So how do we know? Well, we say we do not know because we do not really know how it's wired, but we can find the probability of how John and Mary's friendship can sustain. And the way we look at it is we can look at the expected numbers of edges between John and Mary. So we know John has 3 friends, Mary has 2 friends. So, all right, 3 times 2. But if you look at all the other nodes in your graph, they all have many friends, right? So you need to divide it by this 2 and m, and this will give you the expected numbers of edges between John and Mary. And you can use that to estimate the friendship between John and Mary.
I see. Thank you.
The only thing that I want to tell you is sometimes people look at it and say, okay, I understand this part. If this part is large, the expected number will be large. And I also understand this part. If you have many links in the graph, the expected number will be small, right? But why do we have 2 here? So why do we have multiply here? Why can't we just use ki plus kj? And I will tell you the easiest way to validate this is to sum up all the expected numbers of edges in every possible pairs in the graph. And the summation of the expected number should be the number of true edges in the graph, right? For example, if I say a lottery, you can win a lottery for 1 million, and the chances to win is 1 million over 1 million, 1 over 1 million. And what would be the expected value for this lottery to you if you are purchasing the lottery ticket? That would be 1 million times 1 over 1 million, right? So that would be $1. And if we look at 1 million people or 1 million tickets, the summation of their expected number will be what? Sigma I start from 1 to 1 million, and just add 1, it will be 1 million. right? The summation of all the expected numbers that you can generate it will be 1 million. So that's here. The summation of all the expected number of edges for every possible pairs in a graph should be the number of edges, true edges in your graph. And this is easy, right? You loop through every node. You loop through every node again because you need a pair. And if you look at this, you can start from node 1 and node 1, then node 1, node 2, node 1, node 3, and so on, right? But eventually you are going to get into the situation that this one is node 2 and this one is node 1. So 2, 1 and 1, 2, you count it twice. That's why you have to divide it by 2. And this is just the expected number we wrote here. And if you just expand this using this, you eventually have something like this, and you have an n. Okay, so that's the expected number. So what does the expected number has to do with your modularity? When we are calculating the modularity number, Q, we are looking at each community, and we are counting the edges within the community, and we are counting the expected number of edges within that community as well. So it becomes something like this. You have 2m, you want to know because you want to normalize it, so that your Q number will be between -1 and 1. And this is for every community, right? For every community, what we want to do is we want to find a pair of nodes. So I and J, and we are looking at this. What is this? This Aij is 1 if I actually connects to J, right? If there is actually a link, and 0 means there is no link. And what is this? Well, this is your expected number of edges between I and J, right? We show how to calculate this from the last slides. So if you sum this up, this is your modularity number. This modularity values will be within the range -1 to 1 because you have 1 minus 2m. So why are we divided this to 2m? Well, first, here, you count it twice, so there's a 2. And because you want to normalize everything to -1 and 1, so you have an m here. All right, so modularity numbers is positive if the number of edges within the group is larger than the expected number, right? If you look at here, the only time this will be a negative number is you have a 0 here. Oh, well, you can have a 1, but it's also have a large number, but this number is never going to be larger than 1. So it's a positive number if the number of edges within the group is larger than your expected number, which means here is positive. And if we have your modularity number between 0.3 to 0.7, this usually implies you have a significant community structure. That means if you look here, within each community, this is good, positive numbers. Okay, so this is just a heuristic, well, empirical number. So how do you actually use this? Well, the way you can do this is, remember in our Gerber-Newman examples, you have to cut the line, the edge with the highest betweenness number, and you might want to recalculate your betweenness number, or you just keep cutting, right? So the way to use modularity is every time when you can cut it, you calculate a modularity score for that setting. Then you keep going, you say, all right, I cut this again, and I calculate the modularity score. I cut here, I calculate another score, and then you plot the graph. You find the setting with the highest modularity, and you can use this one as your final result. So again, this is also very time consuming because you want to test every case and generate the modularity number. But it's a really cool data exploration method to look at your graph. Your homework assignment will also need to implement this modularity concept as well. All right, so that was our Gerber-Newman approach and modularity. So this modularity concept is very useful. It's not just useful for Gerber-Newman approach. You can use it as an evaluation matrix to evaluate different graph partitioning algorithms to see if they would generate a community structure that has a high modularity score. So the next topic we are going to talk about is spectral clustering. So this is also very, very useful and common approaches in partition graphs, so in graph theory, but also in image processing, computer vision. This method is also very useful, and I'm going to show you how. So we want to partition the graphs. The problem here is we want to partition a graph to minimize the number of edges that connect different components, right? We want to minimize the number of edges that we want to cut, because if we remove them, we are going to have communities. And we have a goal. Our goal is to minimize the cut size. But this goal is questionable, right? So remember what exactly is our community? Well, our communities should be densely linked clusters, right? And this goal does not express that. So the problem becomes, if you just join Facebook and your goal is just to minimize the cut, we are going to cut you because you only have one friend. And we are going to cut that link and we'll say you are your own community, and the entire Facebook without you is also one community. And we don't want to do this. We want the components or the communities to be equal size or not too unequal in sizes. For example, if we look at this graph, we're going to use this graph many times. So we are also looking at undirected graph, and we are going to focus on by partitioning tasks. That means we are going to divide the entire network into two groups. And in this case, we can cut here, and you have group 1 or cluster 1 or community 1 and group 2. Right, so you can have community A and community B. So two questions we want to answer. The first question is, how can we define a good partition? What does it mean, a good partition? Remember, a partition is a cut. So for example, I can also cut here, right? I say this is a partition, so two disjoint group. Is this a good partition? Well, maybe not, because the sizes of the two communities are not similar. So we want to be able to formally define a good partition. Then once we are able to define that, we want to be able to efficiently identify that partition. So here we go. What makes a good partition? A partition will divide nodes into two sets so that the cut is minimized. Well, the cut is the set of edges that we want to remove so that we can have two communities. We also want the two sets to be approximately equal in size. So set A and set B should be equal in size. We want to maximize the number of within group connections, right? This is important because we are going to look for densely connected communities. We want to minimize the number of between group connections. So this one is actually here, right? So in general, I want you to be able to explain these three criteria of a good partition. So let's look at one example. for this example, if we only minimize the cut, okay? So what is a cut? Again, a cut will give you a partition. A partition means you're going to have two disjoint communities. And to evaluate the cut, it will be the number of edges we have to remove from the graph to have that partition, right? So if we just minimize the cut, the best choice will be to cut edge, because edge only has one link to see. But we do not want this partition because this is too small compared to this entire community here. It's better to use the cut with BD and CG. So this is also a cut give us two partitions. So this cut give us this one partition, two communities, community A and community B. So it's better to cut with BD and CG, and as we know, the smallest cut is not necessarily the best cut. So in the graph cut algorithm that we are going to introduce here, we're going to express partitioning objective as a function of the edge cut of the partition. And if we look at the definition of the cut, this is the set of edges with only one vertex or node in a group. So that looks like this. What does it mean? If we say in this partition, we have A community, we have B community, what are the edges? What edge has how many nodes? Two nodes, right? What are the edges has the two nodes in different communities? Well, that'll be this edge because this is in A, this is in B. It'll be this edge because it's in A, this is in B. So your cut is the summation of all the edge weight. And in our case, we're looking at unweighted, undirected graph. So this is 1, and the cut is 2. So for our example, you don't have to care about the weight, you just add 1. Okay, so this is your cut size. So now we have defined this function. In the graph cut criteria, as a minimum cut algorithm, this algorithm will minimize the weight of the connections between groups. So its goal is to minimize this cut function, and it will generate some partitions that we do not want, like cut here, right? Cut here, community, community, and we do not want this. And the problem of this is because the minimum cut algorithm only consider external cluster connections. What does it mean? Well, if we cut here, community 1, community 2, and this edge is our external cluster connection. And your minimum cut algorithm only cares about minimizing this cut. So it's only cares about these external connections. It does not consider internal cluster connectivities, so it will not give us the optimal solution like this. What would be an optimal solution? The optimal solution is the algorithm that we are going to talk about called normalized cut. This is in a landmark paper in 1997 for computer vision. This is for semantic segmentation. This is a very cool paper. You need to read it. I think I have the link somewhere, but I will show you the link. So normalized cut algorithm wants to be able to partition a graph so that the groups or the two communities in the graph will have similar density. If you look at the graph cut function, target function, it says, sorry, normalized cut function, it says normalized cut. I want to penalize large cut, right? Because I want to minimize this. So this has to be small, this has to be small. and I have volumes here. I want the volume to be large, right? Because I want to minimize the overall function. I want the volume to be large. And I'm doing this plus this so that these two volumes would have similar size. So why do we want to use this criteria? Well, there are many, many different ways you can design this target function to fulfill the goal, right? But why do we use criteria? This criterion will produce more balanced partition. That means your volume in graph A, in community A, and the volume of community B will be very similar. And if you look at the definition of volume, this is the total weight of the edges with at least one endpoint in A. So because we do not consider weight, so this is basically the total number of edges with at least one point in A, right? The number of edges in A. And how do we efficiently find this partition? This is an NP-hard problem. But we are going to look at an example, and we are going to get into the algorithms that will be able to help us find the optimal solution. But before that, let's take a 10 minutes break and come back at 7 p.m. If you have any questions, please leave it in the chat and I will answer them when I come back. Okay, I'm back. All right, so we were talking about the graph cut and normalized cut algorithm. So that's here. So we are talking about the normalized cut algorithm. We say the normalized cut algorithm is going to minimize this function. And by minimizing this function, at the same time, we can minimize the number of cut to generate the partition. We can also maximize the volume of each community as a result of the cut, right? So a cut, you have two communities, and we can also maintain that these two communities will have equal size, right? So that's here. So let's look at one example. Say this is our old friend, our graph. Our best cut is here. And let's look at this normalized cut function. We say the normalized cut for S and T, S is one community as a result of this partition, and T is the other community. So say if we choose this cut, your S community will contain node H, your T community will contain all the remaining node A, B, C, D, E, F, G. And the cut, we already defined this cut function. We know that the cut ST is 1, right? Because we are cutting 1. And the volume of S is 1, because this is the number of edges with at least one end in S. Which edge is this? This is your HC edge, right? This edge has one end in S, the other end in T. So volume of S is 1, volume of T is 11. So how do we get 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are all the edges have at least one node in T. All right, cool. We have volumes, we have cut, so we can calculate this target function based on this. And your normalized cut is 1/1 plus 1/11 equal to 1.09. Let's look at different partition. If we cut here, what is the cut ST? Anybody? Or if you cut here, your cut ST contains how many edges? 2 edges. Great. So BD and CG. So cut ST is 2. And what is the volume of S? 1, 2, 3, 4, 5, 6. Volume of S is 6. Volume of T, 1, 2, 3, 4, 5, 6, 7. So volume of T is 7. So you can see that this cut gives us 2 communities with similar sizes. And the normalized cut function for this partition is 2 divided by 6, 2 divided by 6 plus 2 divided by 7 and 0.962. And this is smaller than 1.09, right? So we want our target function to be small. This is not arbitrary. If you don't remember, think about this. We want our target function to be small because we want the cut to be small. We want the volume to be large. Okay, so cool. This is just one example of the normalized cut result. But the real question is, how do we find this cut? Right? There's many ways you can cut it. How do we know this is the best cut? Well, this is an NP-hard problem. To be able to solve this problem, we're going to look at varieties of different matrices and use the matrix property to help us solve this. Now this is the more difficult part. So now we want to look at matrix algebra to help us find good graph partitions. And this entire approach is generally called the spectral clustering. And we're going to use 3 matrices to describe different aspects of a graph. We're going to use adjacency matrix, degree matrix, and the Laplacian matrices. So I'm going to show you these 3 matrices. But the general idea is we are going to build this. Then we can use all these matrices to get a good idea of how to partition the graph from their eigenvalues and from the eigenvalues and eigenvectors of the Laplacian matrix. So we haven't talked about this yet, but just keep in mind. Before that, we want to look at eigenvalues and eigenvectors. Remember when you first came to the class? Oh yeah, this moves. Very cool, right? When you first came to this class, I told you that this is probably the most advanced math that you would use in this course. That's eigenvalues and eigenvectors. If you are not familiar with eigenvalues and eigenvectors, let's look at one example. Let's say A is a matrix, V is a vector, right? Vector as a direction and a length. If A multiply V equal to a lambda value times V, what does this mean? Well, this means V does not change direction, right? Because the lambda value will only change the length of the vector. For example, if we are looking at the 2-dimensional plane and we're looking at the transformation matrix A, so a transformation matrix will transform a vector, and it can rotate a vector, it can scale a vector, will make it longer, make it smaller, or a translation, it can move the vector around, like a transformation matrix. The transformation matrix A would be able to preserve the direction of some vectors. So this will be the vectors in purple and the vectors in blue, if you look at here. Right, if you wait for the animation, you can see that the blue and purple vectors, their direction does not change. One is this direction and the other one is this direction. Although their length might change, but the direction does not change. But for the red vectors, both their direction and their length can change. Okay, so if we write it down, it looks like this. Transformation matrix, apply on a vector. It does not change the vector's direction, but it could change the length, which is the lambda. And in this case, we are saying that for matrix A, V is A's eigenvector, and the corresponding eigenvalue is lambda. Okay, so this is just the definition of eigenvalues and eigenvectors. And this property is actually very useful. This tells us something about the matrix, and you can even say this V is the signature, one of the signatures of matrix A, and you can use it to do many things. We are going to talk about this eigenvalue and eigenvectors later as well in the PageRank lecture. But for now, this is the basic definition you want to know about eigenvalues and eigenvectors. This is in your high school math. I'm sure everyone did eigenvalues and eigenvectors at least once some time ago. But if you are not sure about the eigenvector and eigenvalues, here are 2 links that you can read. All right, so enough for eigenvalues and eigenvectors. Let's look at these 3 matrices that we are going to use. The first one is called adjacency matrix. This is your graph. Adjacency matrix is also a very important matrix that you can use to describe a graph. This is an n by n matrix. N is the number of nodes in the graph. So you have 6 nodes, n by n. And the value indicate the existence of an edge between two nodes. So in this case, between for the same node, you have zeros. There's no link connect the same nodes. But for node 1 to node 2, do we have a link? Okay, so 1, 2 has a link, so you have a 1. 1, 3 has a link, so you have a 1. 1, 4 does not have a link, so you have a 0, and so on. Okay, so you use 1 to indicate there is a link. You use 0 to indicate there is no link between any pairs of nodes. And you can see this part is the same as this part. So it's a symmetric matrix. This is important because for symmetric matrix, their eigenvectors are real vectors, vectors of real numbers, and they are orthogonal. Orthogonal means the dot products of any pairs of their eigenvectors will be 0. So orthogonal, if you are in two-dimensional space, it looks like this. Okay, 90 degrees. And if you do a dot product, you are going to have a 0. So this is important property that we are going to use later. The second matrix that we are going to use is called the degree matrix. Again, degree matrix is n by n, 6 by 6. And we only use this part, the diagonal part of the degree matrix, and the diagonal part is going to store the degree of every node. So if you look at here, node 1 has a degree of 3, right? Let's verify. 1, 2, 3. Node 5 has a degree of 3 as well. So 1, 2, 3. Node 6 has a degree of 2. So it's 1 and 2. All right, cool. Degree matrix. Now the last one is the Laplacian matrix. Well, the Laplacian matrix is actually just the degree matrix minus the adjacency matrix. So the reason that we want to calculate or we want to store the degree and adjacency matrix is just because we want to calculate this Laplacian matrix. So it looks like this. And you can, if you remember, the diagonal part in the degree matrix is the degree of every node. And for the adjacency matrix, the diagonal part are all zeros, right? So again, here are the degrees of every node. And what are all these numbers? Well, since you are taking a minus sign here, negative sign here in the adjacency matrix, so 0 still means there is no link between 1 and 6. Minus 1 means there is a link or an edge between 1 and 5, right? 1 and 5. One thing that's very cool about this Laplacian matrix is the summation of each row or column will be 0. So if you look at here, 3 plus minus 1 plus minus 1 plus minus 1 will be 0. 3 plus minus 1 minus 1 minus 1 will be 0. 2 plus minus 1 and minus 1 will be 0, right? This is not coincident. This is by design because this 3 indicate the number of edges that at least have one node on node 1. And these are all the edges that link to node 1, right? So node 1 has 3 links to other nodes in the graph. So you have a degree of 3, so that you have 3 minus 1 here. So in this case, your Laplacian matrix will have a trivial eigenpair. A trivial eigenpair is when your eigenvector has all ones. And your Laplacian matrix times multiply this eigenvector be equal to 0. And in this case, your lambda is 0, right? Your eigenvalue is 0. So why is that? If you look at here, this is 0, eigenvalue equal to 0, 0 times x is 0. So why is that your Laplacian matrix multiplied by a vector of all ones will give you 0? Well, this is again by design, right? So if you want to multiply here, 1, 1, 1, 1, 1, 1, right? This is 6 by 6, and this vector x is 6 by 1. And the result should be 6 by 1, a vector. How do we get the first component of the vector? Well, we take the first row in the Laplacian matrix. We do a dot product of this x transpose. And because you have all ones here, that means this dot product is basically summing up every component in this row. And we already know that summing up every component in this row will give you a 0, right? By design, this is the degree, this is a link, and a link. And if you look at each component, it will be doing exactly the same thing at different rows. So eventually everything will be 0. So that's this 0 here. And this 0 also tell you the lambda is 0. So this is the eigenvector, and this is the eigenvalue, okay? Because the vector does not change direction. So important properties of the asymmetric matrix, again, is the eigenvalues are non-negative real numbers. Eigenvectors are real number vectors, and they are orthogonal, like this. So what does this has anything to do with the clustering or the partitioning? Well, say your input is a graph. You can calculate the Laplacian matrix because you know the degree and the adjacency matrix. Once you have the Laplacian matrix, you can use a software package, Python library, to generate all the eigenvectors of this matrix. So later on in other lectures, we are going to talk about how to calculate eigenvectors and eigenvalues. But for this lecture, just treat this as given. You can use any math package to find all eigenvalues and eigenvectors. And once you can find them, you ignore the eigenvector with the smallest eigenvalue because this is trivial. Every Laplacian matrix will have this one. We just take the secondest one. And this one actually tells us how you can partition the graph. This is like magic if you look at here. You look at the sign of the components in the eigenvector. Remember, your eigenvector is 6 by 1. And now you have 3 positive signs, 3 negative signs. There is an obvious partition based on the sign. You say node 1, 2, 3 are in the same partition. 4, 5, 6 are in a different partition, like this. Okay, then you are done. You finish your partitioning task. All right, that's it for today. And next time I'm going to explain this to tell you, I'm going to explain why this works. But before next time, you should read this paper so that you have a better understanding on what we're going to go through next time. Okay, all right, so it's your quiz time. You can go to your Blackboard to find your quiz number 7. And to celebrate the daylight saving time, you have 10 extra minutes, so you can have until 8 p.m. to finish your quiz. Any questions, guys? All right, please turn on your camera. And start to work on your quiz.
Hi everyone, thumbs up for the quiz, and I will end the meeting now. Please remember to upload it on Blackboard.